Begin. Can you all hear me?
Yes, we can hear you.
Okay. Okay.
Yes,
So,
I can hear you, sir.
yeah, go ahead. Any question? Okay. Okay. So let's continue. So last time we saw some basic properties of tensor product, and today we'll use this to compute in some examples. Yeah. And then maybe talk about how it behaves with respect to exact sequences. Okay. So these are some basic properties. If you tensor the ring with any module over that ring, then you don't change the module. A tensor B is same as B tensor A is isomorphic, and these isomorphisms are natural isomorphisms. Yeah. A tensor B tensor C is same as A tensor B tensor C, so associativity, and behaves well with respect to direct sum. A plus B direct tensor C is same as A tensor C plus B tensor C, and it behaves with so localization is of a module is same as tensoring with the localization of that ring. Yeah. So and finally, if you have an ideal I, then in R, then R mod I is same as R mod I tensor M is same as M mod I. Yeah, so these things will help us compute this. So last time, I think Soumyadeep had asked this, Z tensor Q. So of course, over Z is of course Q because, you tensor any Z module with Z, you get Q. What about the second example? What do you get? Z mod 15 tensor Z mod 12?
Yeah,
Zero, right?
Yeah, zero?
No,
Or
Z mod 3Z. Z
Oh,
mod
sorry,
3Z.
yeah.
Z mod
BCD,
3Z.
yeah, whatever the BCD. Z mod, BCD, M and Z.
Yeah, so if we apply, so we can apply number 6, right? So with ideal, maybe 15 or 12, whatever you like. So this is Z mod, yeah. So today this is a bit acting up. It's like a bad chalk. Z mod 12 Z modulo 15 Z mod 12 Z. Yeah. So this, if you like, is same as 3 Z mod 12 Z. So and this you can show is isomorphic to Z mod 3 Z. Okay.
You are using 6, right?
I'm using what?
The 6, I mean.
Yeah. This is YS6. Yeah. Okay, and this is via whatever, usual quotienting and stuff. Yeah, so this is what you get.
You can also use 5 to prove it because you can localize it at some other prime other than 3, and you'll get one of them is 0. So, right?
Yeah, so you can try to show this more directly as well. Is that what you're trying to say?
No, I was saying that you can also use 5 to see it because you can localize the thing at some other prime other than 3, and then you get one of them is 0. So tensor is 0. I mean.
Okay, so maybe there is other, yeah, so I don't know, localize it.
Yeah, one thing, it is not equal to Z mod 12Z modulo 15Z by 12Z. It is 15Z times Z mod 12Z, right?
Same thing, right?
Yeah, what I mean is the ideal generated by 15.
Yeah.
So which is same as ideal generated by 3 in this ring.
Yeah.
That's
Same thing. Same thing. Yeah. Okay.
Yeah. So if you like, this is what you are saying. Yeah.
Yeah.
Yeah. So you get Z mod 3Z. Okay. So this will usually be so you can do this more generally. So maybe Z mod NZ tensor over So this you can try to show yourself. Z mod mz is going to be isomorphic to Z mod GCD of n comma n. Yeah, because it's again Z mod n modulo Z mod m, but that computation comes out to be GCD of these two. Okay. And what about the third one?
M direct sum m n times, right?
Yeah, so m direct sum n times, which is basically n copies of n. So I don't know why I have to overwrite 5 times to get these numbers today. So yeah, m direct sum m n times. Okay. So so this is what you get. Any particular computation you want to do? More examples?
One thing is that maybe you can say that if you tensor with Q, then all torsions vanish, just on just the contortion person.
So you do Q tensor over Z of Z mod some NZ, let's say. Then this is this is even more remarkable. Yeah. So if you try to do using the construction, this seems some crazy thing, but this is sort of zero. Yeah. So
Yeah, tensor of any divisible group with some torsion group is always 0.
yeah. So how do you show this?
Yeah, because every element has a nth order, then you pull the n to the other side.
Exactly.
Yeah.
So this you don't even need these properties. You can use the basic tensor properties. Yeah. So A tensor. So you have you have some rational number A tensor some guy here. I don't know, maybe um, um, k bar, let's say, so where k is some integer. Yeah, then this is equal to a over n n tensor k bar, and then you move n to the other side. Yeah, so this becomes a over n tensor n k bar, but n k bar is 0, which is a over n tensor 0, which is 0 of the module. Anything tensor 0 is 0. So any arbitrary element you have shown is any arbitrary generator you have shown is 0. Yeah. So since this tensor product is generated by such elements, this module must be 0. Okay. Or you can use number 6 again. Yeah. So this is you can also think of this as Q tensor. Sorry. So Q yeah. So this you can think of it as Q tensor Z over Z mod NZ is Q mod NQ by 6. And NQ, as you know, is same as Q. So NQ means the image of multiplication by n on Q, but multiplication by n is surjective on Q. Yeah. So this is 0. So this equality is by 6, and this equality, you know. Yeah. So so if you tensor with this guy, you get 0. Okay.
Or you could use, 5 again, because Q is just Z localized at 0. So Q tensor any module is just M localized at 0. So all torsion must vanish, because whenever you localize at 0 at some multiplicative set, all the annihilators just become 0.
Yeah, you localize at 0, meaning you invert all the non-zero elements. Yeah.
Yeah.
So in particular, you invert n.
Yeah.
So yeah, so you can use 5 as well. Okay. So any other example you want to take a look at? Something. So maybe one example which may be useful is
Yeah,
what.
can you give an example involving polynomials?
Yeah, exactly. So that's what I was going to do. So kx is a polynomial ring in one variable. Okay. Tensor it with ky, another polynomial ring in one variable over k. So I'm using different variable just so that there is less confusion. Yeah, I mean technically you can write kx here, a polynomial ring, polynomial ring in one variable, tensor over k. Yeah. So this is actually isomorphic to kxy. Yeah. So okay. So this may. Okay, so this I guess one has to show somehow. Yeah, so we'll use the universal property to prove this. I don't think we can, these basic properties will give us. But once you prove this, then you know how to, and so if you have a polynomial ring in 3 variables and you want to tensor it with polynomial ring in 5 variables, then you get a polynomial ring in 8 variables. Yeah. So so let's try to do this. So we want to show that this isomorphism. So we'll give a bilinear map from kx cross ky to kxy. So this is the reason we didn't write kx tensor over kx. Yes, so that the notation doesn't look bad. Yeah, but even if you write kx, you get polynomial ring in 2 variables. Just that the 2x's is difficult to distinguish. So what is the bilinear map? So you take a polynomial f and a polynomial g and send it to, what should you send it to so that it becomes bilinear, natural one? So there may be many, but we are looking for
FG, right?
f times g. Yeah.
Product. Yeah.
Yeah, the product. Like we did in I don't know, integers. Yeah, integers over integers we were doing. So this is bilinear. Yeah. So p is clearly bilinear. Yeah. So this you can just check, or whatever from experience in vector spaces, you know that this is going to be bilinear. So in k bilinear. So we are doing tensor product over k. Yeah. So so it defines a linear map, a k linear map. So we get a k linear map from kx tensor ky, call it theta, to kxy, which will send f tensor g. So f is a polynomial in x and g is a polynomial in y. Yeah, f tensor g to fg. Yeah, so maybe I'll use x and y so that it looks a bit better. Yeah, psychologically. So fx gy. So what it goes is fx times gy. So as usual, remember, I mean, in elements of this left-hand side are not exactly, are not just this, but sums of this. Similarly, in polynomials, we know that every polynomial is not in 2 variable is not of this form. Yeah, it's sums of this. Yeah. So there is hope that this will be an isomorphism. So this is k linear. Yes, I've already written that. So you get a map in one direction, and then you can give a map in the other direction. Yeah. So kxy to kx tensor k ky. So remember, yeah. So I hope you know that giving a map. So this will be more like a module at the moment. Yeah. K module. No, but it's more than that. It will be a ring homomorphism. So, but one has to give a ring structure and so on. Yeah, but let me just say. So what is the map in this direction? So what you do is given a polynomial fxy. You can write it as, I don't know, a0 plus a1x plus a2y plus. So you'll have to separate things out. Yeah.
We have to think of
Yeah,
it as a
we need to
polynomial in
monomial.
y, right?
Say that
You can
again.
think of it as a polynomial in y, then map to that polynomial in y, right?
No, just send it to monomials, right? Just send the
Yeah. So
monomials
I
to
was
tensors,
gonna.
right? X and y and send it to x and tensor one.
Yeah. So the point is, if you decide once you know where for a ring homomorphism, this is okay. Yeah. So once you say where x and y goes, you can for polynomial ring, then you know where the rest of the things go. So we want.
Yeah, but you
So
wanted a K module homomorphism, so maybe okay.
yeah. So so you send x to x tensor 1 and y to 1 tensor y. Okay. This is the map. And so so the point is, this is so. Let me just argue that this is also so this of course is a k module, this kx tensor ky, but it's also a ring. Okay. So so giving a ring homomorphism from a polynomial ring to another k algebra or k mod. So you know what a k algebra is? Was that done? So polynomial rings you have seen, right? Giving a map from a polynomial ring to another ring. Was that where those concepts?
Yeah, we have to. Yeah.
So those concepts were covered, right? So if you have a ring R and you have a ring mapped R to A, and you want to give a ring map from Rx to some this ring, then all you have to say is where X goes, and then you are done. Yeah, so then it extends linearly. So so anyway, what I can do is one can just define it this way. Yeah, so X goes to this, Y goes to this, and then you know how to extend it. Yeah, the way to extend it is just send any polynomial in this way. Yeah, so summation ai j x power I y power j, you send it to summation aij x power I tensor y power j. Yeah, so then this map is fairly is explicit. Yeah. Because x tensor 1 times 1 tensor y, I mean, the multiplication here is not clear, but that will be the multiplication. So for all that, there is more work to be done. But let's just define it this way. Yeah, so this is our map. So that was theta, yeah, so this may be theta prime. Define it this way. So then we have to check that this is a k-linear map. So check theta prime is k-linear. But that is straightforward. Yeah, if you multiply something here, it will I mean, everything is a k module. Yeah, so theta prime is k-linear. And this map is now completely explicitly defined. So there is no issue of well-defined and so on. And so now you just check whether this is an isomorphism or not. Yeah. So write it bigger. So theta compose theta prime of summation aij x power I y power j. So this is finite sum, yeah, because it's a polynomial. Is summation aij x power I tensor y power j. So remember, such elements belong to our tensor product. Yeah, and this sorry, not theta, not just this, but theta of this, which since theta is I linear, this is summation aij theta of x power I tensor y power j. But theta, our map theta is such that it sends f comma g to f times g. Yeah, so fx comma fx tensor gy to fx times gy. So here fx is x power I and gy is y power j. So this is aij x power I y power j. So this is what you get is theta compose theta prime is identity, and similarly theta prime compose theta is evaluated at maybe generators. You can look at the generators. Evaluated at fx tensor gy is as it says, is theta prime of fx times gy, and this I mean, so maybe so in fact not just arbitrary so in fact we know that x power I and y power j will generate for as I and j varies overall natural numbers will generate this on this left hand side. So we just have to check for these, and for I y power j, which is same as x power I tensor y power j. Hence theta compose. Hence, okay, stuck. Hence theta prime compose theta is identity on x power I tensor y power j I j greater equals 0. This, but this generates, yeah. But this generates kx tensor ky. So if in fact you take any generating set of this left module and any generating set of this module on the right, and you take all possible tensors between these two sets, then that will be a generating set of the tensor product. Yeah. So we get that this is indeed a isomorphism. Okay, so now you can also say that once you have this thing, then you can also define the multiplication using the multiplication on this polynomial ring. Yeah, that is maybe that's the most simplest way. Yeah.
Yeah, one thing I have to say
Yeah.
is that I can think of kx tensor ky over k as a kx module also, right?
Yeah, yeah. I mean, it will. It is a kx
So
module as
basically,
well.
yeah. So ky is a k module. Then you're extending the scalars from k to kx. So kx module, and on the right hand side, the k adjoint x comma y, that can also be thought as a kx module. Kx module. So as kx module, these two things are also isomorphic, right?
Yeah. They're isomorphic as rings, then it's isomorphic as so that's stronger than all this other isomorphism.
Yeah. Right.
Yeah. So isomorphic as kx module means just multiplication by x. It behaves well with multiplication by x.
Yeah.
Isomorphic as rings means it behaves well with respect to multiplication within. Yeah. So once you say that. Okay, so maybe I'll just state what Samedeep and even last time I talked about. So somehow I started doing something stupid here about localization. I should have been doing things about tensor product. But okay, so maybe I'll just write it here. So say phi from B to A or A to B be a ring homomorphism. Be a ring homomorphism, then B is an A module, yeah. So this you know. In fact, B is called A algebra. If you are, so this maybe in fact B is called an A algebra. So A algebra precisely means this, yeah.
You define A dot B as phi times B, right?
Yeah. So okay. So maybe so not very familiar. So let's just say A dot B is phi A B for A in A and B in B. Okay. So this is what this B algebra looks like. So I'll clean this up later. Okay. So somehow, but anyway, so hopefully I wrote it so that it will be a bit faster for us. But I wrote the wrong thing. Okay. So what we get is so once you have this, then now yeah. So maybe this part I have written. So yeah. So I'll take care of this thing later. But now suppose M is a, so look at this thing, yeah. So suppose M is an A module, then B tensor A over M. So B is an A is also an A module as we mentioned there. Yeah. So when I do this. Okay, this wasn't a bad idea. Keep it. So this part I wrote. So B is also an A module and M is also an A module. So when you do the tensor product, what you get is an A module. Yeah, but it's also a B module via this map, via this structure map. where S is this guy. Yeah, B times B prime tensor M is B prime tensor M. But to prove that this is a structure map, what do you have to do? What are the properties of the module multiplication? So you have to show that S1 comma. So you have to find an S such that it happens. Yeah. So the properties you need is S1 comma alpha is alpha for all alpha in B tensor A over M, and you have to also show that it behaves well with respect to addition and multiplication and so on. Yeah. So as of B plus B prime comma alpha is S of B comma alpha. So maybe instead of writing this SS, I'll just write the usual thing. So we want B plus B prime dot alpha is B alpha, B dot alpha plus B prime dot alpha, whatever that multiplication is. There's some typo here. This should be M. And we want B dot alpha plus alpha prime is B dot alpha plus B alpha prime. Yeah, so these are the three and associated. So and B dot B prime dot alpha should be same as B prime, which is an element of the ring, dot alpha. So all these should be true for all B prime in B and alpha prime in B tensor. Okay. So we want such an S. So to cook up such an S is a bit of a task, yeah, because you can't just say, just send this to this. That doesn't define the whole map. As we know that elements of B tensor M is a bit are sums of this. So technically you have to use this bilinear. So what you do is to define such a map for each. So for each, so the way one does is that for each B in, so maybe I'll try to below. Yeah. So to do this, what one does is that for each B in B, you define a bilinear map CB from B cross M to B tensor M over A. This is well defined. Yeah. So giving a map to the tensor product is not a problem. Giving a map from it is an issue. So what do? You send B prime comma M to B prime tensor M. Okay. So again, you can check that CB is bilinear. Yeah, it's linear in the second variable immediately, and even in the first variable. You're just multiplying everything by B. Yeah. So CB is bilinear, and so you get it leads to, let's say, theta B from B tensor M to B tensor M, which will send B prime tensor M to B prime tensor M. Okay. So now you define S of B comma alpha to be basically theta B of alpha. Okay. So theta B exists for all B in B. Yeah. So this is how you define your structure map. Yeah. And then you can verify that each of these properties is true. Check. as satisfy module properties. So this is how you can show that B tensor A over M is also a B module, and it's B module in a natural way. So so multiplying by an element of B is just multiplying on the left coordinate.
So previously it was a A module, and you are extending the scalars, right?
Yeah. So B tensor so M was an A module, and B tensor M over A is obviously an A module by construction, because tensor product of two A module is A module, but we also want to view it as a B module.
Yeah.
And this is how you show that it is. So you want to define, say that this natural map which you are trying to define is actually okay. Yeah? So it extends to whole of tensor product. Okay.
And M is sitting inside B tensor M as 1 cross M, we can think of, right?
Say that again.
I mean, M is sitting inside
It
B
not
cross
sit inside
No,
there.
no. There is no sitting inside here. Yeah.
It will not sit inside there.
So maybe is there a map? Yeah. So maybe one can write a map or something.
Yeah, there is a map, but yeah, it's
I
not
mean, a
indicated.
map from M to B cross M.
B tensor M.
B tensor M as M goes to 1M, and I think this is.
Yeah. So maybe there is a module. So there is a linear map from
A linear, yeah, A linear.
from M to B tensor M by sending M an element to M to one tensor M. Yeah. And whether this will be injective or not is not always clear. Okay, so these things are rarely things are injective, but of course, if B is a nice enough guy, then it will be injective. But,
and this may not be made to be bilinear, right?
Because M is not a B module, right? So you can't talk about bilinearity. Bilinearity only if M becomes.
But can you tell us the assumption? Can you tell us if M is an A module and N is a B module, then what happens to the Helm sets, right? I mean, if you extend scalars to M and then take the Helm set there in B.
Yeah, so
what
that's
happens
something to do
set?
with, yes, maybe once we do some home tensor duality, we'll get to it, yeah?
Okay, thanks.
So how home and tensor behaves, then we'll get to it.
For example, Z cannot be made into a Q module, right?
Yeah, Z you can't make it into a Q module.
Yeah.
So in general, okay. Was that your question? So an arbitrary A module you can't make it into a B module. Yeah. Only after tensoring you get a module which you can, of course, is a B module. But and of course, any B module is an A module. So this is how this works. Yeah. So somehow, so it's important even in algebraic geometry how there's push forward and pull back. So, but I don't. But anyway, that will be in master's algebraic geometry, not here. Okay. But
so without tensoring, the extension of scalar doesn't work, right? I mean,
without
that's why we define tensor. Yeah, I think.
Yeah. So that is one of the reason, and the other reason is this polynomial ring. Yeah. So you'll see that. So yeah, this maybe I should say here. So so we will see. Before getting to this exact sequences. So you saw this polynomial ring in two variables is tensor product of polynomial ring in one variable. Now, if you think about it, a polynomial ring in one variable is a coordinate ring of affine line. Yeah. So recall. Kx is, if you like, OA1, yeah, coordinate ring of OA1 over K. And so what we are saying is, and KXY is coordinate ring of OA2 over K, yeah. So what we are saying is coordinate ring of, so this shows in this particular example at least that coordinate ring of A1 cross A1, which is A2, A1 cross A1 is A2, yeah, product of these two affine lines. This is same as OA1 tensor over K OA2. Yeah. So this is true more generally. So maybe this is not too far away from what we have done, but so more generally.
Yeah, O1 came. Yeah.
Oh, yeah, sorry. Yeah. OA1. Yeah. Or more generally, let's say X and Y are affine varieties. Affine varieties. So this is not recall. The recall is this part, and this is what we concluded from that theorem which we proved. Yeah, X and Y are affine varieties. Then O of X cross Y. So X cross Y is also an affine variety, and its coordinate ring is just OX tensor OY. Yeah. So this more or less follows from number 6 and what we have proved about tensor product of polynomial rings. Yeah. So maybe this I'll put it as a homework. Okay, follows from kx1 to xn tensor over k, or maybe not. So I'll see if I is isomorphic to so and one of those earlier properties of tensor product. But I mean, this isomorphism, I'm not just thinking of as isomorphism as modules, but rings. Yeah. So and of course the ring. So if you take two rings and you take the tensor product between them, what you get is again a ring. So this is something which. So it's in this spirit, yeah. This is extending of scalar spirit. And the rings, the multiplication map you give using such trickery. Yeah. Okay. So maybe I'll frame up.
As K modules, it doesn't say much because.
Yeah, of course, it's just a vector space, but so that's why you need more structure. So I'll make this. So I'm not sure if I'll make this as a homework problem, but I'll certainly make this as a homework problem. If A and B are K algebra. So remember now K algebra we have defined is, and that means there is a map from K to A, ring homomorphism from K to A, and ring homomorphism from K to B. So here K need not be a field. Yeah, so it's K a ring. And then A tensor B over K is also a K algebra. So you already know it's a K module, but okay, but it's a ring as well. Okay, so that's what you'll have to show. So you have to define multiplication in some, and then this is a ring homomorphism. So this is as rings or K algebras, K algebra homomorphism. Okay. Okay. So The goal today was to go to tensor product, short exact sequences of tensor product, how tensor product behave with short exact sequences, and we are off from it by a mile, and whatever I wrote is useless. So, so let me just. So I don't know why I wrote about localization. So, so let me do it afresh here. Okay. So. So what we want to show is that let f from A to B be a linear map of our modules, and then and M be an R module. Then tensoring with M, F tensor M from A tensor M. So then there exists a natural map this from this to this, which has some nice property, which is R linear, which is R linear. Satisfying functoriality. Functoriality, which means if G from B to C is R linear, then G tensor M followed by F tensor M. These, so the G tensor M is going to be a map from B tensor M to C tensor M, and so first apply F tensor M and then apply G tensor M. So this is the right order, is same as G composed F tensor M. Okay. So this is the first statement, and the second statement is moreover, if A to B to C to 0 is an exact sequence of our modules, then with F and G here, then A tensor M to B tensor M to C tensor M. So I'm not writing R below, but because there's only one ring involved here, is exact. So so I have not put a 0 here on the left below. So F need not be injective, but even if F were injective, it won't stay injective. So so caution. Even if F is injective, F tensor M need not be injective. So of course, I mean, we are going to get tired of writing F tensor M in the proof, so we'll call this F tilde, and this as G tilde. F tensor M by F tilde and G tensor M by G tilde. Okay, so so let me do some part of the proof, at least define the map, and maybe the tensor product part we'll do next time if there is no time today. So yeah. Okay. So proof. what is this map? So I have to give a map from A tensor M to B tensor M. So as we know, it's difficult to give a map directly. So we give a bilinear map. Yeah. So one way to think about this is that there is a I mean, giving so bilinear maps from A cross M to any module is in bijection with R bilinear map from A cross M to any module is in bijection with R linear map from A tensor M to that module. Yeah, so there is equivalence of category, if you like, category theory. So what is this map? Bilinear map. So phi from A cross M to B tensor M. What we do is send AM to FA tensor M. Yeah, so this element in the target exists, so this makes sense. And check again that phi is bilinear, R bilinear. So linearity in the first variable follows from the fact that R is F is R linear, and linearity in the second variable is just straightforward. Yeah, M is an R module is what linearity in the second variable means. Okay, and properties of these tensors, the structure the map B cross M to B tensor M, that is bilinear. So this is hence phi induces F tilde, and this is our map from A tensor M to B tensor M, which is R linear. And what does it do? It sends these special elements to these special elements in those modules. Yeah. So little tensors, little a tensor, little m to these guys. Okay. So that so this takes care of this getting an I-linear map, and then its functorial is also straightforward. Now note that if G is a map from B to C, and then G tilde from B tensor M to C tensor M will send little b tensor M to G of little b tensor little m. Yeah. And so since these elements generate the module, F tilde and G tilde is determined by what it does on these things. Yeah. So now, of course, G composed F tilde by definition, G composed F tilde by definition is a map from A tensor M to C tensor M. And what does it do? So on the special guys, so we do have this induced map. We want to say that this is same as G tilde composed F tilde. Yeah. So G composed F tilde, what will it do? It will send A tensor M to G composed F A tensor M. Yeah. And of course, G tilde composed F tilde of A tensor M is also G tilde of F tilde F of A tensor. F tilde of A tensor M is just F of A tensor M. So these are some immediate checks. Yeah, and G tilde of F A tensor M is just G composed F of A tensor M. Yeah, so they agree on a generating set. So G tilde composed F tilde is equal to G composed F tilde, since they agree on generating set. Okay, so that that completes the first part. So is there time? So maybe I'll prove prove the whole thing, or at least okay. Let's see if I can. So maybe surjectivity is what we'll do. Okay, of G tilde. So so to show G tilde is surjective. So maybe I'll just go here. To show G tilde is surjective, it's enough to show that all the special element, a generating set of C tensor M is captured by G tilde. Yeah? To show G tilde is surjective, enough to show C tensor M belongs to image G tilde for all C in C and M in M. Yeah, because if it contains the generating set, it contains the whole, the image contains everything. And so, but that is okay, because G tilde of but G is surjective, so there exists B in B such that GB equals C, since G is surjective. So G tilde of B tensor M is C tensor M. Yeah. So this proves G tilde is surjective, and of course, since G composed F tilde is G tilde composed F tilde, and G composed F is 0, and maybe another observation, a trivial observation is 0 tilde is 0, because the 0 map, if you take the 0 map, F of everything is 0, so it will be the 0 map. Yeah, so implies that image of F tilde is contained in kernel of G tilde, because G tilde composed F tilde is 0. And so the three properties above tells you that the G tilde composed F tilde is 0, and that tells you that the image of F tilde is contained in kernel. So finally, we want to show the other inclusion, and hopefully that's not too bad as well. So let's take something in the kernel of G tilde. So okay. So maybe this will require a bit of work, yeah. So this maybe I'll do in the next class. Okay, and we'll begin with this, and hopefully in the next class we'll wrap up the discussion on tensor product. Any questions so far?